So I have good news and I have bad news for the remainder of your labs for this semester. The good news is we have a really nice test bench for you to use for your labs and for testing of your labs for the rest of this semester. The bad news is we have a really good test bench for you to use for testing your labs for the remainder of this semester. And I thought it'd be useful to kind of give you a brief introduction to what the test bench and the testing framework is attempting to do. And you have to experience it for yourself, but this at least can help you get started with regards to this whole new infrastructure that hasn't been there for the earlier labs this semester. I'll start with saying that this has only been tested on the VDI remotely connected machines that you have access to for your labs this semester. You should be able to get this to work, just like many of you have been able to get ModelSim to work on your own machines if that's what you want to do. I'm not going to really support it though. So this I know works. Uh, if you are having trouble with your dependencies for this, and the main dependencies are just some Python 3 version, any version should do, ModelSim, and then the Quartus software for synthesis, um, you're kind of on your own. But in terms of updating this to work on your own machines, it is doable. We have to update it every semester already. You take a look at this, and there's just a number of scripts for you to be able to run. Depending on where you have the files, it may give you a warning when you try to run it. But the starting point would just be running this test framework. It may warn you that this is on a network drive and that's dangerous. And it's all starting with a Mars assembly a simulation to begin with. So we would have to provide it first an assembly file, and you may get sick of typing in this example. So copy paste it if you don't want to type it over and over again. You're providing it to start with an input assembly language program. This is definitely a step up, right? In the past, we're just setting our waveform inputs to be able to sort of emulate instructions. Here, we're providing it a series of instructions in a .s or .asm file for us to test our design with. It shouldn't take too long. It's going to first compile that in Mars. It's going to check to make sure that your VHDL design for your processor actually compiles as well. And then it's going to simulate both in Mars as well as in ModelSim and determine if there was any discrepancies between those two simulations. And in the version I have by default, what it's also doing is it's also going to open up ModelSim separately so you can look at your signals. But if we look at the output here, this is what you want to see by the end of project part A. Victory, your processes matches Mars expected output with no mismatches. It's going to be doing it cycle by cycle. And I'll walk through a little bit about how it's doing it. We don't need to know all the really tiny low level details, but you have to have a good conceptual understanding for what's happening. I talked about earlier in the semester how, ultimately your design is going to have a lot of signals in it, and you have to really get a good feel for how do you keep track of all the signals in your design. And this is about as complicated as it's going to get. So, you're looking at a decent number of signals that you'll be testing. The trick is knowing which signals to look at and why, and then working backwards from there. So you have to be pretty fluent in your own design. The extra complexity hurdle for this assignment is you also have to gain this fluency in this test bench that you yourself are not creating, that we have created for you. That's I was kind of jokingly saying it's good news and it's bad news. We have a very nice test bench. You have to understand how to use it to successfully complete this assignment. If we take a look at what is happening in the test bench, there's not that much going on. So we start with just the .bat file, and in the .bat file, we are just setting our path to Python, and we're telling it to run this test framework.py file. I added this deep debug option as a default. That option is just what opened up ModelSim after the fact to let you look at your signals. If everything works successfully, you never need to look at that. It's only when you have a bug or two that it's useful to be able to open that up and directly take a look at what is happening. We take a look at test framework .py. The main algorithm is what you are going to be following here, and the code does it for you. But we start with looking at Mars, and it actually runs Mars in the background for you. So in the first place, you need to make sure you have a piece of code that actually compiles properly and runs properly and does something meaningful in Mars. Just because we have this .bat file that you can double click and run doesn't mean that should be your starting point. If you're wanting to test something in your processor, the first step is what is a useful test case from an assembly language perspective for my processor design? Create that offline, confirm that that works in Mars, that does what you expect it to do. Store that somewhere so that this script can find it. Run Mars Sim. Next, it's going to compile your VHDL files, and they have to go in a very particular directory, but you can take a look at the directory structure for that. Compile your VHDL. Well, you want to make sure your VHDL compiles before you run the script as well, right? It should correspond to something that's roughly correct based on your understanding, and you're running the script when it's time to test your design ultimately. In the Mars simulation, it not only runs the Mars and logs the output, it also uses that compiler to then just check and generate what the instruction memory should be. And it uses that same .hex file format we started using in lab number 4 to initialize the instruction memory, so we should get a one-to-one comparison. And that's ultimately then what this script is doing. Using the test bench we provide for you, that VHDL, it's going to generate a log of what writes to processor state are happening on a cycle by cycle basis. And when we talk about correctness in the context of this course, it is doesn't match the output of what Mars is generating for that same sequence of instructions. In terms of those of you who want to edit this and use this on your own machines, you'll find a number of sort of hard-coded paths to where ModelSim is installed and where Quartus is installed. Just do a search for place in the Python files. It's not the most modular, beautiful written piece of code in the world, but it works. And update that to where your installation is. This is only tested and confirmed on the VDI machines. Um, the ModelSim script itself is just running the simulation and comparing the result and checking to see what the log looks like here. We actually have a little bit of code here as well that's checking that, did you actually change the test bench? So I may get the question later on that my code works, but only if I radically change the test bench to do something different. And that's not allowed. And the script will actually tell you, you've changed the test bench. When the TAs or I review your code and evaluate it ourselves, we'll be using the original test bench for that. I've said enough about it. Let's take a look at the actual test bench file itself. It's not so different from what we've already been doing, right? This should look pretty familiar with how we're just resetting the processor, how we're generating a clock for our design. We have our top level port map, and that's the first thing that you may notice a little different. We are already telling you, here's what your top level design needs to be called. Here are the ports that it needs to have. You are not to be changing this file. This file is a given, and you're working from within it. And as I mentioned in class, there's not going to be a lot of ports on your top level processor. Clock and reset, and then the only reason we actually added any other signals is that so that synthesis tools don't automatically eliminate code that it think isn't needed. As in that demo previous in the semester that I showed you, that if it notices that signals aren't actually being observed in your design, the synthesis tools, Quartus, will just eliminate all that logic. We don't want it to eliminate your entire processor, so we add ports for observing the ALU output and also ports for our instruction memory write, so it doesn't delete the entire instruction memory in our design. So that part is given to you, so it's a little different, but otherwise it's no different than any other structural port mapping. Our process that resets and generates the clock is the same, and then now this part is a little bit different. So there's a separate process whose only job is to confirm for every given clock cycle whether or not there's been any state changes in our processor design. And this is a little different than what we've done before. So it's generating a log file essentially. If a signal called regwrite is high on a rising edge of the clock, that means we've written to our register file, log the actual value that's been written to the register file. Likewise for data memory. If there's a memory write happening in our design, log that memory write that happens. So the end result of this simulation in ModelSim is just a sequence of text strings depicting for each clock cycle what has changed in the processor, what is updated in the processor state on a cycle by cycle basis. In order to do this in a design that you yourself are not modifying, we do have to make and enforce certain assumptions about your design. And don't fight us on this. This is just what is needed for this to be consistent across all the projects. There's signals like regwrite and memory write, and those are internal signals in your design that you need to then support in your design. So this is an alias signal. That memory write is actually a signal inside your processor called s underscore dmemWrite. You need to have a signal called s underscore dmemWrite and use that as your write enable. You may want to call yours something different. That's fine. You have to at least map it to this signal for the testing framework to work. And so when we look at our MIPS processor.vhd file, the underlying processor implementation where you're going to start adding your code, there's a lot of to-dos slash don't change this here. You need to have these signals in your design, and you need to use those for their intended purpose for the testing framework to detect that instructions are being executed, that register file values are being updated, and or that you're writing to your data memory. So this helps in a sense that I'm telling you, here's what you need to name these signals. It also I understand is a little bit restrictive in that, well, you may have wanted to do something completely differently, and you still have to map it to this naming convention that we have here. Otherwise, this should look a lot similar to your Project Part A design. We have our component for our data memory. We have to start doing our port mapping here for our instruction memory and data memory. And to do, put your whole processor here. And that I understand is going to take some time for you to do that, but that's where your code would start here, and you don't need to touch the rest of it. One final gotcha that I'll describe now, but I understand it'll be a while before we run into this issue, is we have to detect when is our program done. In Mars, we know our program is done because we call that very specific syscall instruction with a value in our V0 register. Right at the end of your code, you set 10 into V0, and then you call syscall, and that's your terminate. That's your suspend instruction, your suspend syscall. Our Mars code that you're running is going to have that at the very end. We need to tell our model simulation that yes, that is the equivalent to us being done. Stop simulating in model sim, stop our test bench effectively, and be done and start to do our comparison at that point. And that's what's happening in this design, that we have this signal called shalt, which the test bench is also potentially reading as well that we need. And that's specifically doing exactly that. This is just our overly complicated data flow syntax for this, in which we're saying if the instruction is a syscall, which is a very specific encoding for that, and the actual value of your V0 register is 10, then we're in a halting condition. So that's another signal that you'll need to implement in your design as well. A V0 signal that is actually connected to, and that's what this to do is applying here, should be assigned to the output of register 2, your V0 register, for that component of your simulation to work. So we are restricting you a little bit in terms of what this design is trying to do. It makes testing very nice and easy. If you've implemented a new instruction, create a .s file, a Mars simulation, a MIPS assembly test file that just tests all the conditions you're interested in, test that it does what you expected to do in Mars, and then this should all just kind of automate. And it allows you to either confirm that the instructions do what you expect them to do, or conversely, gives you a feel for what may still be broken in your design. But in order for this to work nicely for you, it does have to follow this way of doing things. So let me know if you have any questions. Let's separate out the questions that are, I can't get this version of Python on my laptop. You can put those in the technology channel in Discord. But if you're having questions about how to use this, that's perfectly appropriate to ask in the Project B channel in Discord. And I do expect until we all get familiar with this over the next week or so to have lots of questions about how to get this to work. Why is the window disappearing on me? Why am I just getting an error? I shouldn't get an error. I should be able to help you debug those things pretty quickly because we do have a pretty good feel for what this script is supposed to be doing. So good luck with that. Let me know where you have any questions, and I'm looking forward to seeing your single cycle processor designs.